Today, our lecture will be the topic about validation, cross-validation and hold-out method that we've seen previously. And yep, there's some information that you probably knew about last week. I think it's about up to here. And what we will learn will be around from here to here. And there will be some model selection scores, those AIC, BIC that you've seen in the code. And yes, there are details about those scores, which I think you can go back and read them yourself if you are interested in. But I will give you some rough idea around maybe topic number 7, right? And actually what's the main point today is going to be like number 6, about the data splitting. Okay. So we've said before that actually when we train our model, right? Initially, if the model is too simplistic, it's too easy. Let's say you use few number of model parameters, what you will get is often you get high bias. But when your model become more complex, what you will get is probably high variance, but low bias, right? But initially when you start training, like whatever model you're having, like it either be that simple model or complex model. In your initialization phase, when you start training, you will get high error, which could mean that you get the high bias and high variance altogether. And in fact, you cannot tell whether or not that value of errors came from bias or variance unless you actually compute that term. So what I'm trying to say is that the fact that when we say, when you train your model for too long, you get high variance, your model become overfitting and all that, are mostly speculation. But if you want to know for sure whether or not your model is behaving with high variance, you have to compute it and separate it as a terms. And that's actually a practice that I've seen in many researchers, they've done it. Like they usually have this bias compute, they usually have this variance compute independently to see what is actually dominating. Okay. And yes, when you have very complex model, as in high, using lots of model parameters in your machine learning, what you will get is, yes, of course, your model could behave exactly like your training, right? So you have very low bias for sure. That means your whatever trainings is definitely fitting your ground truth data set that is split for training. But the thing is, when the model is that complex, the problem is that you may have hard time to interpret what's going inside. And of course, if you've been training for too long, what you will get is that your variance will be definitely quite high, and that's due to the fact that your model starts to be overfitting, right? But again, the complex model will give you that flexibility to capture the, I would say, like odd behaviors inside your data, especially the data-driven model. So that is like why when we say that, deep learning could do most of the things, it usually means that you have lots of data. And sometimes those behaviors cannot be correctly captured with some mathematical model. So your best bet is to use some data-driven approach. And that's the reason why. It's flexible. It could be used on various types of maybe, any weird behaviors of your data to, you can use them to capture those behaviors. But the thing is, it could be very complicated, so it's hard to interpret what's going inside. So that's why these days we have special tools like RedCam or maybe some AI explaining, some explainable AI to look at what's inside. But on the opposite side, if your model is too simple, okay, you can simply interpret what's going inside. But the thing is, your bias could be very high because if your model is too simple to capture that characteristic of your data. Okay, so that's kind of like a trade-off between the complexity and the simplicity in your model. And yes, from last time, what we've learned is that, okay, we have some, measurements of goodness or those evaluation techniques like mean square error that we've learned last time. We also have some residual sum square, R-square statistics. These statistics can be used to capture the performance of your work. But the thing is, if you use them purely on your training, and as I mentioned before, your training model, if it's really being accurately coded or implemented, whatever is going to happen is that your model will always perform better with the higher number of iterations you run, or maybe with more amount of data. It will only get better. But you will not know when it's fitting too much to your training data or when the overfitting is happening. So that's the reason why when you come across these evaluation techniques, you can use them to gauge if your model is being trained in a way that you expect. But you also need to run it on the validation dataset to see if your model is getting overfitting. So these are scores that you need to, calculate the validation score for them. So I would say it needs validation. Because it could only evaluate the fitness, between your model and your data. So that's why I said that it's actually the measurement of the goodness. It's like how good it is to fit your data. How well, okay, I'll put this again. It fits your data. But it cannot account for how complex your models become. So that is like the bad points of these evaluation. Cannot tell, you have to highlight the word cannot. Because today, there are going to be the evaluation rubrics that can evaluate how complex your models becomes. Namely, they are those scores that I wrote here. These scores can evaluate not just the fitness, but also how complex your models become. And that's the reason why in our coding session, if you look at the code, when I calculate this score, I only use just the training data. Because there's no point using the validation. It doesn't give me like an insight to what is the fitness. Right? It can tell. I mean, if your model is behaving quite well, your validation could help. But to me, it's just like, okay, what's the point of looking at that when actually, what is better is to look at the validation score of the goodness of fitness, right? And when that validation just start to increase, then I know that it's fitting too much. It's just harder to integrate when you use it with the validation. Yeah, that's what I see. So usually, this score you'll be just fine. Just use them. With training. But it will tell you pretty much nothing during the initialization phase, or maybe if your hyperparameters are getting, unwell. So pretty much that's the reason why I would recommend just use them with the training, because it's fundamental enough for you to see whether or not your model is behaving correctly. And also because it has another term for complexity, that's why it's compensate for the fact that if your model is getting too complicated or overfitting, this complexity term will tell you whether or not it's too much or, good enough. Okay, but for RMSE, just to recap, R square, RSS, or this guy, you need both training and validation. You need it in training to tell if your training phase is working. Training. You need it both in training and validation. Okay? So these are about scores. But another thing that we go through today is about your data splitting. Okay. So, yep. This is the kind of topic that we will learn today, but we can skip this because I think we all understand what the validation is. Okay, so as I mentioned before, if your green line is like the line for validation, it could be for your testing as well. If you notice that your, the line of your validation performance, initially it will start to decrease, just like your training, that means everything's going well. But when your validation line starts to increase, that means you should stop, because that is when your model starts to get overfitting. This is just to recap. But the thing is, how many types of data splitting that we can do, right? What we've seen in the code, there are just one type, it's the holdout technique. But in fact, there are 3 types. So the holdout is simply, you just divide the data once, right? But for k-fold validation, which is what I will ask you to do in your homework, that is, when you have different way to shuffle your validation and training. In other words, this is like the first trial that you shuffle your data. This is like the second trial that you shuffle your data, where the blue are your training and the yellow is your validation. So if you keep shuffle like this, what you will get is that you will get, let's say, for example, if you shuffle it for, let's say, 5 times, you will get 5 validation performance, right? Which is different from your previous setting, that is the holdout. You get only 1 validation performance and maybe 1 training performance. But this one, you will get 5 validation and 5 trainings. What you will do after that is that you perform what we call average. So if you average all your validation score and training score, what you would see is that you would see roughly, like if you shuffle your data, are your model is your model performing better as you run? So if you validate them, that means that if one of the batch have a very good selection, it fits in every, your assumption and your model is working pretty good. So you definitely have like a low validation error, right? But then, if another shuffle happen to shuffle and pick the bad validation set, then you have that high validation, right? And maybe you can have a high again. That means there's only one shuffling that gives you the best validation. That means that your model is actually fitting to this setting, but not the rest. So that also means the generalization is not good enough. Okay? But if you start to have more low validation in the shuffling, and maybe more low, that is signifying that your model become more generalizing towards your cases. And that is when, it starts to perform well. But what you would see is that you probably see initially all are high, and then after a number of time of your training, it will start getting low, and then it will start to get high again. When it becomes high again, that validation simply means that your model are fitting towards certain cases. So that is why k-fold cross-validation would actually be the solution to the homework that you're having right now, because you have about thousands of data. And every time you shuffle, you may not be lucky. Sometimes you get a bad set, sometimes you get a good set. And that is the reason why k-fold cross-validation could work well in this case. But of course, if you have 10,000 or hundreds of thousands of your training data, can you afford to do that? Well, it depends, right? It depends on how big your computer is. But if your computer is like a generic normal size, like in this laptop, you probably don't want to do that. Actually, another extreme is what we call leave one out. Leave one out is pretty much like you have one sample only for your validation, and the rest is used for training. And you pretty much just randomly select that sample. So this is like the extreme case, when you just use one batch of your data, or maybe just one sample of your data to be your validation. And I do not recommend doing this, because this is pretty heavy, like for no reason, right? Because your data will eventually fitting towards the rest anyway, but of course, it will tell you on this small fraction whether or not it's getting good or not. But it's meaningless. To a certain point, it's meaningless. So you may consider doing leave one out if your data sample is extremely small, like 100. I mean, no more than 100, maybe. Because just imagine this means you run it for 100 times, right? And 100 trainings. Okay? So actually this is one of the main goals that we have to learn today, and probably you can try using each of these techniques in your homework and see what's the difference between using k-fold and hold out. Actually, I have already gave you the answer already. So yeah, you probably know the answer, but you have to describe in your homework with your evidence. Everything that you provide in your homework has to come with the backed up evidence that is your experimental result. Otherwise, I will not give you the score. Okay. And this is an example. When you run hold out, if you use hold out, and as I mentioned before, if you each time you run it, you will get inconsistent results, just like the plots here, that sometimes you get high, sometimes you get lows. That's because, it depends on which batch you random, which batch that is random in your case. Meanwhile, k-fold, you will likely get a consistent result each time you run. You can try it with your homework. By consistent, I mean just look at the final plots. And that's consistent because don't forget that each of the curve, each line here, actually came from the average of those k-folds. Each line. Okay. And here I do it 7 times running. So that means if I have 5 folds, each line came from 5 folds, averaged. And then I repeat the experiment 7 times. That's what this graph means. So that's why I get a consistent result. Versus the hold out. Hold out, there is no such fold. The performance that I get is like 1-1, right? But here, look at the x-axis. X-axis is the hyperparameter settings. So in this, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 hyperparameter settings. So this is what the graph look like. Yeah. Okay. And leave one out. Just imagine you split your data like for each of them, and you average each of them. Therefore, your average result will look nearly the same for each runs you make. So that's why you get a very consistent result. And actually, this is one of the questions that I've asked before in the midterm. Just tell me which performance curves are from holdouts which curves definitely from, but not, I think it's not going to be this graph, but some other performance evaluations. But it's just like for you to gauge. Why? Because when you do your job in the future as data scientists, definitely one thing that you have to do is to help your colleagues find the bugs. And if you get this result, can you tell where it came from? It's like working backwards. It's simple, I know. It's like compared to the rest of the course that you've taken for the whole entire 4 years, it's like one of the simplest yet. I know. That's why we're gonna take the exam in class. So this is a summary of that cross-validation technique. You have hold out, K-fold, and leave one out. So yes, in terms of computation, hold out is simply the lowest because you just do it one sampling and one run. That's it, right? But K-fold depends, but could be feasible because that depends on how you're gonna separate the data into each sampling steps, right? But leave one out is definitely too high, right? Very high. And yes, there are a number of samples, and these are the number of samples in training versus the overall, I think, or maybe the number of folds. Okay, but don't worry, it's not that, but it's just like for you to have some ideas about what they are. It's not, in the exam, it's not going to be like you fill up the blank of this table. No, not like that. Not that hard, right? Anyway, that's actually all for the session of cross-validation techniques. Any question? No, not yet. All right. And we'll go over this last topic on the model selection score. There are actually those scores that I provided in the code, and actually what I just described previously. They are the scores with complexity. They are these scores. Okay. Right. So model selection scores are scores that have loss function, which is used to measure how well your model is fitting the data set. Or in other words, it's like more testing your fitness. And another term that is the model complexity. And that we learned before that complexity somehow goes together or maybe can agree with variance. That variance term in your BCE, MSE. So that's why sometimes you can use just the model selection score independently. But I honestly don't recommend this technique in practice. But as we have to learn about them, we will just learn what are those scores, because in some cases you may find them useful. Especially, I think it's especially useful if you don't have large amount of data. And if you don't have like a good technique to find what is going to be the complexity or the attributions to the variance. And sometimes you can actually come up with these scores yourself, especially if you know what is measuring the fitness. Let's say if it's an RMSE, and you could just add them with some complexity measurement term. But you have to make sure that they scale in the same range. That's it. Actually, you can use that as same types of indicators, because the indicator in the model selection score is simply just measure the fitness and the complexity of your model. And in fact, it's kind of resembling your bias and variance in a way, because if you remember the bias term, it's actually your prediction minus your ground truth square, right? So this is like the loss function. And your variance is somehow going to normally increase with your model complexity. So it's reflecting with the mean square error. but not the same, because this time your variance is not variance, but its model complexity is different. So yes, the best model is the one with the lowest score, especially if your loss function is representing the error and the model complexity representing, let's say, maybe number of parameters. So that is simplest formulation of it. Okay, let's look at each of them. So yes, suppose you are using a likelihood or maybe a loss function, right? Because it's a likelihood, that's why we put in the negate sign. If someone remember the log likelihood kind of form, is a log likelihood is a log of your forecasting versus something like that. So that's why you need a negate. Or you can just imagine the fact that if this is high, that means your prediction fits well with your data. But what you want is a loss. So you want something that showing, the error between them. That's why you would rather provide a negate sign. Right. Or it could be y same. Whomever in the front is the same. Mm-hmm. Okay. I think the one on the top is the likelihood, and the one at the bottom is the posterior. But don't worry about that. Anyway, okay. So for all the likelihood term, if they're like a log scale of the probability, you have to put the negate sign. Scale by 2 is usually happen, especially if your probability is being Gaussian. If you remember, the exponential term will have that -1/2. So that's why we have that 2 and negative, right? To turn it into like a loss function. And n, as I mentioned before, the second term is the model complexity. In this case, n is the number of parameters in your model. For example, if you look at the linear regression, the number of parameters is like the number of linear weights that you use them to compute the regression. For example, if your fx is defined by a1 x plus a, let's say I have more than one feature. Okay, maybe x2. I think in the example there were like 8 of them. So you can imagine, okay, that was a linear combination of 8 terms. Right, no bias. Yeah, okay. Let's say no constant, like don't have this term. So there are going to be 1, 2, up until 8. So n will be equal to 8. That is the number of parameters in here. And the fact that they scale by 2 is because they want to compensate with the fact that they just scale by 2 on the loss up in the front. That's it. And actually, all of the laws are having this kind of formulation. Like there are losses function, which I will highlight. Don't worry, we will make it in time. Loss function, right? Actually, this is, if I remember correctly, this is another loss. But I didn't provide it here. Somewhere it was in here. Anyway, this is r squared. These are the loss. And the complexity are the term that comes afterward. N is the number of parameters, and M is the number of your training sample. Which normally you will use them if the number of training samples that you have are low. Why? Just imagine, if M is large, right? If M is large, this term is definitely go somewhere like 0. Like that is also 0. Log of large term, in fact, this one will go to infinity. But normally this means that, okay, if it goes infinity, there's no point having this term. But usually we have them, we need them only if they are low, when the number of samples are low. Usually they just use them for that reason. That's it, I think. And in fact, you can have a look at, okay, let's just look at this example first. In this example, it's like the example where we try to do data fitting with parameters A and cosine functions, A, B, and cosine function, and then we have X as our input data. And we try to feed in our X into this function and try to make sure that not that function, sorry. Try to fit X into this function and make sure that that Y hat capture Y. But the thing is, because it's like a toy sample, so in fact, I also generate a value of Y using this formulation. There are some noise in my measurements because there are E. That's it. Just example of what our data look like. And thing is, I can use those evaluation to gauge, what are the number of parameters that I should use in order to fit this model with this ground truth curve that I generated. So let's say I have generated the ground truth data. That's it. Yeah. Okay. So as we vary the number of parameters and compute each of these, so you can see there are some tendency that initially these have a very high loss, right? So that means the loss is higher than the complexity to the point that it doesn't compensate, even though you have low complexity already. The loss is still high, that means the error is still not acceptable. But when your loss decrease, that means, okay, this number of parameters is probably okay, and the loss is now low. And then, as you increase the number of parameters, again, this becomes high. And usually this is high because the number of complexity will start to dominate your term. Or maybe the loss that you have happened because, okay, but we put this way, if we are doing this on our training, the loss due to the fitness will not increase. But the only loss that will play important roles is going to be the loss due to complexity. Okay. And again, the R square, you have to be careful because R square, the higher the value, the better it is, the fitness it is, right? And we have R square and adjust R square. So this example only show you that the adjust R square, they actually have this additional term that account for model complexity. And the thing is, what surprised me is the fact that that complexity term happens to help reduce the error such that the value of adjust R square is closer to 1. So that is something. You can further analyze what may be happening. But anyway, this is just something that I noticed about. Maybe because M is very large. If M is very, very large, this term will go to 1. So that means it's equivalent to not having the impact towards the R square. Yeah. And Lastly, there was CP, Mallow CP, which is another score, this one. But don't worry, I think these are just like example of the scoring system that you could use. Okay, last one is your MSE. And because as I mentioned before, MSE only contains the loss due to fitness. There's no complexity whatsoever. Therefore, that's why you need one testing and one training. I mean, training and validation. Or it depends, like if you want to do 5-fold cross validation, then that means these line came from averaging 5 times. If you do just hold out, this means this line, each of these line, came from just one time of running. Okay, just don't forget that fact. And the rest of that, I encourage you to go back and read the lecture yourself. But don't worry, it's not going to be an exam. It's just describe how would you use each of these score to select a model. Maybe just a little bit about analyzing, which I'm thinking, how should I go about this? Some of them are deriving like how it comes to this point, like how we came from this probability and then come up with this loss. It's actually come out from the KL minimization, and it's like how KL minimizations turn out to be a problem of maximum likelihood. Yeah. And after that, it talks about how would you use this score and say which model is better than which. But we will continue about this next time. A little bit about how each of these score came from, but it's not much. You can read it yourself at home before starting the lecture next time on Wednesday. And on Wednesday, we will go over linear regression, the technique. Okay, that's all. Thank you for your attention today. See you on Wednesday.